on this one. Okay, so we're very happy to have Dimitris Papailiopoulos among us. I know Dimitris for a long time. I know him for a long time because I knew when he was a grad student, but it's not too long ago. In a short period of his independent academic career, he has already made pretty significant marks. So he is an associate professor in University of Wisconsin-Madison. He works on information theory, distributed system, large-scale machine learning, and also lottery ticket hypothesis, which we are going to learn about today. He graduated from UT Austin, where he was advised by Alex Dimitris, who many of us remember because he gave a talk only like 2-3 months ago in the same seminar. And Dimitris, I mean, he's a star in all of these fields. He has got multiple awards, including the IEEE Signal Processing Society Young Author Award, the Joint Communication and Information Theory Society Paper Awards, many other paper awards, the NSF Career Award, and multiple teaching awards. But I think the reason I really respect Dimitris is because very rarely you see one person who has already, there are 3 or 4 very solid work that you can just remember, right? So for Dimitris, I can point out a few of his papers that I have read, and it's like I don't have to look at his CV and say, oh, I know this 3 or 4 papers in my heart, because this is the very significant, nice, concept that he has introduced in these papers. I don't know that many people in his generation has this ability. So we are very happy to have Dimitris. The floor is all yours, please.
Wow, what a generous introduction. Thank you so much, Arya. I'm also like really happy to be among friends and colleagues. I would have enjoyed it much more if this is in person, and definitely Rainsec for a future visit, hopefully in February during ITA, but we'll see. So yeah, today I want to talk to you a little bit about the research that my group has been doing for perhaps the past couple of years, where we try to understand a few things about the lottery ticket hypothesis, which perhaps some of you may have heard, but I'll go into detail about what this is. This is, of course, joint work with a bunch of great collaborators from UW-Madison. And I want to start this off by something that you've probably already seen. We all know that the sizes of models are completely out of hand. For example, if you follow sort of like language model type of trends, we know that by now there's like every year there's a model that's like 10 to 100 times bigger than the previous year. For example, there's a Megatron model that has 530 billion parameters. It's a big number, right? So it's like huge models. Perhaps this may be unavoidable. There's been a lot of question about whether this scale is important. And there seems to be a lot of evidence pointing towards this perhaps hypothesis that increasing the number of parameters seems to somehow help optimization and learning, like both of them at the same time, which is pretty bizarre and perhaps counterintuitive from a traditional learning theoretic perspective. All we've seen so far is just bigger models doing better things, but perhaps not faster. So the major challenge is, in fact, the compute, storage, and memory footprint of all those, models. If you want to do anything algorithmic, even inference calls for many of those models, this is very expensive. And it's also a challenge for research, right? So when you hear about all these breakthroughs in language models, we're like, oh man, I wish I could like train, I don't know, like a GPT-3, and you just can't do it, right? We've reached the point where even building infrastructure to train those insanely huge models can be, as prohibitive as, I don't know, building your own Hubble telescope or whatever. So we're at a point where, research itself is somehow limited, right, by the fact that these models are so huge. In terms of like perhaps more operational stuff, even, if you want to run something at an edge device or, anything that's like, I even consider my laptop an edge device, anything that's not, 100 GPUs, it's just really hard. So perhaps the question to ask is if there's any leeway, if we can mitigate some of that scale, if we can reduce some of that scale. People have been thinking about this question for a long time, right? So the answer to that is perhaps we can do some type of a model compression, maybe throw away some of the model parameters or compress the model in some way. And the way that we usually compress models is the following. So you want to minimize some form of a loss, if you will, between the source model that you're going to compress and the actual model that the compression algorithm or whatever will spit out. And the constraint is that you want that compressed model to be as small as possible with regards to some representation complexity, perhaps it's bit complexity. And there is, if you've done information theory, taken a data compression type of a course, the biggest difference between compressing models and compressing data is the fact that the compressed model has to map features to labels without any decompression or decoding algorithm somehow. So this is quite a difference with regards to traditional bit compression or whatever, where there is a decompression algorithm. Here, there's no decompression algorithm when you try to make these models smaller. So how do we compress models? And, of course, there's perhaps tens of thousands of papers on that. One sort of line of research is to start sparsifying, throwing away weights of the model, or perhaps using low rank matrices, or using kind of a teacher student type of distillation approach, where you try to distill a bigger model into a smaller one. And there's many, many more other things. For the purposes of this talk, I will focus only on sparsification of weights and weight pruning. But a combination, if you will, of these methods can lead in many cases to models that is, 1 to 2 or sometimes 3 orders of magnitude smaller compared to where you start. Perhaps the surprising thing is that not you can compress those models, but you don't have any loss in accuracy. All right. And I want to talk to you a little bit about a particular version of model compression, which is that of sparsification. It's maybe the most natural to think about, or the easiest to think about. And just to say, please interrupt me. I really enjoy when when I talk and it's more interactive. So just go ahead and don't worry about interrupting me at all if you have any questions. And I'll try to pause as much as I can. Yeah, so basically, then we're kind of focusing on this network pruning idea that started back in the 80s. I think, maybe many of you have heard the optimal brain damage paper in the 80s, and that led to sort of a series of different algorithms for sparsifying neural networks. The goal of pruning is to basically start with a neural network that is potentially dense, perhaps your favorite ResNet 50 or whatever, and throw away edges, throw away weights from this network. And the goal is again to kind of make energy, compute, and memory sort of not to be such big of an issue in this case for these models. So how do we do it? I would like to argue that there is a main meta algorithm. That's not the only way that people have been doing network pruning, but one of the a big fraction of the papers on network pruning kind of follow this meta approach, which is to take a model architecture, randomly initialize the weights, train those weights to full accuracy, and then throw away some of the weights according to some rule. For example, you can throw away perhaps the smallest weights in absolute value. The result of that pruning process is the fact that you're going to incur some loss in accuracy. All right, so you're going to lose some of the accuracy of the dense model. And the way to mitigate this is go back and train a little bit more, and then prune again, lose some accuracy, and train and prune and train and prune. So this kind of pruning and training approach has been quite popular in the literature of model compression, and in this particular case, sparsification.
So
any question about this high level idea? Yeah.
Dimitris, sorry, I'm interrupting, as you said. So you can prune only the edges in this method, but not the internal nodes, right? So
perhaps by pruning edges, this would lead to pruning activations or internal loads. There is a sort of subfield, if you will, of this literature. It's called structure pruning, where instead you're sparsifying edges, activations like neurons. Mm-hmm. Yeah, so this is kind of completely unstructured. It only looks at weights. It doesn't look at particular activations or neurons.
I see. Okay.
So did you have another question, Arya?
No.
Okay, good. So yeah, I guess the main thing here is that this approach has a big issue, and the big issue is the fact that you have to kind of train for full accuracy once. So you have to basically incur all the computational effort of training the full model before you start pruning it. And the question is whether you can avoid this first step. Is it possible to perhaps prune earlier during training, not after you fully train the model. And that's where kind of like the whole lottery ticket hypothesis starts. There was a paper in 2019 by Jonathan Frankle and Michael Carbin in iClear that in fact actually won the best paper award, that hypothesized that in the beginning of training, even before you start computing gradients at initialization, there exist sparse subnetworks that if you were to magically find them, then you could train those subnetworks to full accuracy without having to prune them again. So the promise perhaps of this paper is that you don't have to fully train your model before you start finding sparse subnetworks, before you start kind of like, pruning it, all right? So again, the hypothesis is that there exist special sparse subnetworks at initialization. You randomly initialize the weights and you find them magically. We'll see how they find them. And if you somehow are lucky enough to find them, then you can just train those networks and not worry about sparsity anymore, not worry about pruning anymore, all right? And if I were to give sort of like a weak definition of a lottery ticket, it has to be better than something. A lottery ticket has to be trainable to accuracy that is better than training a randomly sampled sparse subnetwork, right? So if you were to tell me, forget about that lottery ticket or whatever, what if I were to just use the same sparsity levels per layer and just like randomly sample my weights and train that random network, what would that give me? So that second technique should be worse than, the performance of a fully trained lottery ticket, all right? Any questions so far?
Okay, so just so that I understand this, when you suppose you have a full dense network and you trained it fully for the best accuracy, and then you randomly sample a subnetwork. Mm-hmm. So your lottery ticket subnet is from initialization, it will be trained better than that, whatever the accuracy that the randomly sampled network would give.
Yeah. Right? So like even so, and I guess the main thing is, and even perhaps simpler baseline is you start at initialization, you find a lottery ticket, or you find a randomly sampled subnetwork. Both are sparse. In fact, both have the same sparsity level per layer, and you train both, and you ask which one of the two is better when it's fully trained. And it has to be the case that lottery ticket has to be better, otherwise it's not special.
Right. So the randomly sampled subnet. Okay. So even if I see. So this means that the lottery ticket just have to be better than a random thing.
It has to be better than random, right?
It doesn't say that it is close to the accuracy of the dense.
Right. So that would be kind of like a stronger definition, like a more strict. And in some cases that that's true, but this definition helps build some baselines that we'll see later. That you have, if you don't beat this baseline, then it means that what you find is not really a lottery ticket, right? So this is kind of like the absolute minimum to be considered sort of, let's say, special, if you will.
Right. So in statistics, there is like many such instances where you just want to do better than a random, because if you can do better than a random, then there is a simple reduction or something that will say, then you can achieve full accuracy or something, right? So
perhaps we'll see something along these lines in a little bit. Not so much with regards to training, but somehow, Anyway, so yeah, I'll just hold on to this.
An empirical version of that. Okay, I see.
Great. So how do they do this? They have an algorithm that's called IMP, the Iterative Magnitude Pruning algorithm, that actually looks a lot like the sort of like the meta algorithm of pruning and retraining. So what you do is the following. You start with your random network and you train for a number of epochs. Once you train for a number of epochs, you prune and keep only, let's say, the top 80% of the weights with regards to their absolute value. Whatever you prune away, whatever you kill, they're frozen to zero. You're never going to touch them again. And whatever weight survived that pruning cycle is going to be rewinded back to its initial value. Okay. This iteration is repeated many times. So again, you train, throw away some weights, whatever survives, you roll it back to the initial value. And you repeat this again and again until you have a target sparsity for your initial subnetwork. The property of that subnetwork is that indeed it will have weights that come from initialization. What is perhaps not as satisfying is that the algorithm you run actually is computationally pretty intensive. Like they see that, train the actual full network is in fact sometimes more cheaper than running the IMP algorithm. But the goal of this paper is not so much to say, here is an efficient algorithm for finding these special subnetworks. Their goal was to say something special actually exists at initialization, and perhaps there's a better algorithm to find it, right? So that was kind of like what initiated study for identifying, if you will, signal at initialization. And what Jonathan and Michael showed in this paper experimentally is the following. So if I were to take a lottery ticket and I run SGD on it, and instead replace the lottery ticket with just a random subnetwork of the same sparsity, lottery tickets train to better accuracies. So indeed, they were more special, if you will, than just a completely random network. And they saw that both sort of like the sub-architecture discovered by the IMP algorithm and the weights themselves matter. Like if you were to reinitialize the weights or re-randomize the weights of this random subnetwork, that would mess up with the performance if you were to train it to full accuracy. And this sort of created a lot of excitement in the area of pruning. This was, I would argue, the first time where people were doing something that early at the phase of training before even starting. And it basically, potentially sort of opens the, perhaps positive scenario of, maybe you can just start with a very sparse network and only have to train that sparse network, right? So the goal of that would be to basically even do, even have training be much faster than it originally was, right? Any questions so far? All right. So
this will this IMP algorithm at the very beginning, this is choosing a random subnet, right? And then starting from, right? And then so this seems to be very much dependent on this initialization, right? So it's exactly like so if you're not close to that lottery ticket, you might never really converge to a lottery ticket. Do you see what I mean?
Yeah. So perhaps So perhaps at the very least there is kind of like some information, if you will, carried by the sort of like the structure of the network that you mine. So hopefully I will answer some part of this in a little bit, but I see there are a few questions. Would you mind? I will read them out. My pointer, but I know there's questions, so if you can just check them.
Yeah, so I think this is related to what I was asking. Are there many lottery tickets, and can you do some sort of warm start, right?
Yeah, very good. Yeah, so we'll talk about the warm start. I will argue that if you can find them polynomially, then there have to be a lot of lottery tickets, right? So the fact that they sort of find them, at least in this case, it means that there must exist more than that. And we'll see in a little bit those arguments. Maybe we'll see them in a little bit more concrete way.
Right.
But one thing that is perhaps quite interesting is the following. So in that original paper had only MNIST experiments, right? So this pretty surprising, right? So there's no way if you were to write something like that now on MNIST you would get the paper in. But there were no ImageNet or whatever, or it's CFAR10. And something interesting happened. So following that work, there were a lot of papers that said, you know what, IMP is expensive. We have a different way of finding lottery tickets at initialization. But what happened is that there were a lot of sort of other papers, kind of if you will, trying baselines. They were saying, okay, you claim to have generated a lottery ticket with some algorithm. Here's what I'm going to do. I'm going to take that lottery ticket, throw away the weights, throw away the architecture, only keep the sparsity levels per layer, and I'll just randomly sample according to those sparsity levels and train those subnetworks to full accuracy and see what happens. And what happened is that for CFAR10 and ImageNet, those random subnetworks were as trainable as a lottery ticket. So the lottery ticket was not special at all. And there's actually, several papers that sort of basically prove experimentally that pruning at initialization does not seem to work, at least in the form that people were presenting it so far. Perhaps the most interesting paper is by Frankle himself. So he basically took a bunch of algorithms, including IMP, and they said, let's do a few tests, right? So let's do some sort of sanity checks. What's a sanity check? Let's take the architecture and kind of re-randomize the weights of the lottery ticket architecture. or take sort of like the architecture itself per layer, take the sparsity pattern and just like reshuffle it, kind of like, change the connectivity and change the weights themselves. If that does not destroy the performance of your lottery ticket, what you find is not a lottery ticket, all right? And that's exactly what happened. So they find that basically all those algorithms that were quite popular early on in the lottery ticket hypothesis literature, they were just good hyperparameter tuners, if you will. They would just find really good sparsity levels, but the patterns themselves and the networks themselves were no more special than a randomly sampled network, okay? And the only fix to this issue was the following. On CIFAR10 again and on ImageNet, the one thing that you can do is you can basically train for a little bit, perhaps break the symmetries at random initialization, train for one epoch, and now then run the IMP algorithm. And they find that this actually helps. Like if you were to run the IMP algorithm a little after initialization, then the subnetworks that you find there are much more trainable in comparison to randomly sampled subnetworks of the same sparsity. Questions? Just pause for like a few seconds to see if this all makes sense. So again, the way that the story goes is the lottery ticket hypothesis paper says there's interesting stuff at initialization. There's sparse subnetworks that if you magically find them, you can train them to accuracy competitive to the fully dense model. Definitely better than a randomly sampled model. And there's follow-up work that said, well, that's not really the case. For ImageNet and CIFAR10, anything that the lottery ticket hypothesis algorithms find are no more better than just like training a randomly sampled sparse subnetwork. Okay.
So by lottery ticket hypothesis algorithm, you mean the IMP?
The IMP and basically any I want to say that any algorithm that kind of like sort of like came shortly after that. So there's like a bunch of algorithms like SynFlow and Grasp and Snip, bunch of other ones that were attempting to find lottery tickets, but they all sort of failed these baselines and sanity checks.
I see. So it doesn't mean that the lottery ticket doesn't exist. It just
exactly
means
right.
that
Yeah, so that's
those algorithms are not doing.
So you're thinking exactly like me. I'm like, I'm curious, do lottery tickets actually exist, right? So forget about the algorithm question. Let's think about the existence. And while I was thinking about these questions, there is this really cool paper that is coming out, which for me was like,
there is one other question. Actually,
yeah, sorry.
So from Ari, in 2019, how was the existence of lottery tickets established, if not empirically?
Yeah. So all right, good. Is the question with regards to the first? Because so what they did is they did find lottery tickets for a MNIST, right? So they said, at least there is one data set and one type of model for which this is true. Therefore, I can hypothesize based on that evidence that this is a more general phenomenon. But then what the follow-up research says is like, well, maybe this is not a general phenomenon. Like maybe it's either like a question of existence, maybe they don't exist for ImageNet, or maybe it's an algorithmic, an algorithmic failure, if you will. So what I will try to convince you in the following is that both lottery tickets exist and you can find them experimentally for these bigger data sets and models. All right. Awesome. Any questions so far? All right. So I want to go back to still experimental results and try to understand the question of like, forget about training. Like, I will not change my weights. I want to understand if there is any sort of signal, if you will, at initialization. Like, what can I do with my initial weights? And there was this extremely surprising paper in 2020, I believe, called What is Hidden in a Randomly Weighted Neural Network. So this is by Vivek Ramanujan and Mitchell Wartzman. And what they find is something quite spectacular, I think. So they start with, a fully trained, let's say, ResNet 34 that achieves some performance on CIFAR10 and ImageNet. And they say, okay, let's keep that network on the side. Let's start with another network. It's a little bit wider, perhaps a little deeper, like a wide ResNet 50 that has completely random weights. And the only thing that I'm allowed to do to that network is chop off some of the edges, chop off some of the weights. So the only sort of power I have in tuning that network is setting weights to off, okay? So they just do pruning and they ask, how much can that accuracy of the model be? And the surprising fact, perhaps, is that by only pruning the weights of a random network, you can get full accuracy on ImageNet and CIFAR10 by only exchanging sort of perhaps, the expressive power of weight tuning with more width. So they say, okay, a little bit wider network, only let me do pruning, random weights, kill off a few things, and I will show you that this thing achieves full accuracy, or like accuracy competitive with like a little bit smaller model, but one that's trained with like, SGD, all right? So I want to like dive a little bit deeper in this with regards to this phenomenon, perhaps explain it a little better, and I want to see if we're all on board with this. So the Ramanujan et al. Paper again says that essentially pruning is all you need, if you will, that state-of-the-art accuracy models or tickets, if you will, they simply reside within random subnetworks, and all you have to do is just prune the random network. So again, I start with my architecture, I randomly set the weights to like Gaussian, Laplacian, uniform, all of these things work. And the only operation I'm allowed to do is like kill off weights, nothing else, like set things to 0. And they find again that like, this works. Like, if you were to allow me to have a little bit more of a parameterization, only setting things to 0 is basically going to be good enough to get accuracy that is competitive with a model that's fully trained with SGD, but is perhaps a little bit smaller. And the way that they do this, I'm not going to go into the details of this algorithm, but the way that they do this is by doing essentially backpropagation on the supermask, if you will, on the 0, 1 kind of like variable of like, what weights do I keep on my neural network. And when I saw this paper, it completely blew my mind, because it still is to this day the only paper, the only sort of technique I know that is not backpropagation on the weights that reaches accuracy competitive with SGD. And the surprising thing is that it does that by essentially trying to approximate like a 0-1 optimization. Like you don't do anything with the weights apart from killing them off, right? So, I'm not surprised anymore because I've read this many, many times, but for like a long time, I was completely mind blown by the fact, and I wanted to really understand this. And the question that I had is like, forget about the algorithm. Is that even true, like existentially? Like if I start with a random network, what can I find at initialization without changing the weights in terms of like subnetworks? Like, can I express functions by just like, finding, whatever, sort of like, subnetworks in that, randomly initialized network? And there's a very trivial answer to that question. If you give me like an infinite network, like, it's something that's ridiculously large, by sheer chance, I can find combinations of weights that basically result in a desired function that I would want. But I want to dive a little bit deeper with this question. Just want to also see again if this makes sense to you.
So they showed this for many data sets and with many different network architectures, and like this is sort of this.
And perhaps the thing to add is that the goal of that paper was not to show that there exists sparse subnetworks. In fact, the sparsity level that defines like around 50%. The goal of that paper is to just see, is there anything at initialization? Like what can you do with just what you're given, like the initial weights, if you're only allowed to prune them? So the networks defined are not sparse. But again, the goal was not like sparsity, just to understand, if you will, how rich is the family of like, sub networks when you just, when you're not allowed to choose the weights.
So, and their algorithm, you said that the way they're setting it to 0 is by doing this backpropagation on pruning super. Like,
essentially,
elaborate? Yes. Yeah, like, can you say a little, like one line more, like what exactly they're doing?
Yeah, so basically think of like having every weight is associated with a survivability score. If the score of that weight is really high, it's going to be included in the forward pass. If the score of that weight is below a threshold, that weight is going to be set to 0. And now there's basically a function that says, there's an indicator function that you have to backpropagate through, right? There's like a discontinuity. And typically the way that people handle this is by something called the straight-through estimator, during which in the forward pass, you compute the model like normally. In the backward pass, you treat the discontinuity as the identity function. So that's kind of like roughly how they do it. I don't know if this sort of answers on a high level the question.
On a high level, yes. So there is one.
There's more details, but perhaps we'll see an algorithm a little bit that maybe will make a little bit more sense.
Right. So there is another question over here in chat from Prem. Does retraining the sparse subnetwork found by pruning and backpropagation improve performance?
Yeah. So is it about this work? Because they saw something really surprising here. So they said, you know what? Let's do this with sparse subnetworks, like, I don't know, 1% sparsity. Take those subnetworks that come out of this algorithm and train them with SGD. And something surprising happens. There is no improvement, almost no improvement at all. So somehow this algorithm kind of like breaks the optimization landscape, and you're stuck at some place that you can't really improve a lot. So you can't really use these networks found by the Ramanujan algorithm as lottery tickets. In fact, they're not lottery tickets, they're not trainable, which was, it's still a spectacular thing. And this is something that the authors tried. And if you go in the appendix, they tried this, and just like there's no improvement if you try to do this.
Very strange. Okay.
Very strange. So let's see. So, I'm kind of like, back in the old days, I was an information theorist. I'm still sort of like, there's a little part of my heart that still kind of like, vibes with information theory. And, what I want to understand first is like, just existence questions, like what can we actually find at initialization? Was this experimental observation by Ramanujan et al. Kind of like a one-off thing, or is it a more universal thing? So I was thinking about this, and in fact, the first time I discussed this with Konstantinos Daskalakis and Alex Dimakis at NeurIPS, the last NeurIPS before the pandemic in Vancouver, 2018. And some ideas were bubbling up, but like during that time, Malak et al. Actually wrote this paper, proving the lottery ticket hypothesis, pruning is all you need. This was a theoretical paper, trying to essentially prove the existence of good things at initialization, right? So here's what they prove. They say, let's assume there's a function described by neural network. That neural network is of depth L, so there's L layers, and the dimension, the width of the network is D, okay? It has some weights, it represents some function, and I would like to ask this question. If I were to give you a network that is larger, could you prune that network to approximate the target function of the original one? So you have a target function represented by a neural network, you have a random network that's potentially bigger, and you want to see if I were to prune the weights of this random network, could I match this target function? And what they basically did is they answered this question to the affirmative. They said, yes, you can actually, by pruning, you can approximate functions, but the caveat is that you need overparameterization. How much? Well, you need the size, the width of the, so if the depth is like only twice as much, so not a big deal, but the width has to be polynomial in every parameter of the network, including the inverse error of the approximation. So the width was pretty sizable, but they said, if that's the case, I can definitely approximate any target function, all right? So this is an existence result, it's not an algorithmic result, but if this is true, this actually kind of proves everything, right? So it proves that like lottery tickets exist at initialization, later iteration lottery tickets exist, like, anything that you kind of like, you can basically prove with this existence tool. Perhaps the only thing that is not matching reality at this point is the requirement on overparameterization. The requirement on overparameterization, as we'll see, is perhaps a little bit too loose. And the reason for that is that the main idea behind the proof is the following. I have a target function, and I have a random network that I'm trying to prune to approximate the target function. So if I were to just like see for every weight, what is the chance of finding a random weight that's kind of close to it, then, that's sort of like, the way that they achieve this, right? So I'll go maybe in a little bit more detail about the proof, but the idea is that somehow if there's enough weights in the random network, then you're going to be lucky enough and find one that is close to the weights of the target network. So that's the high level idea of their proof. And perhaps I'll go a little bit more detail in that. Any questions so far? So one thing I want to say about this is that does not match the Ramanujan result. So like, the Ramanujan paper said, take a network that's like perhaps 5 times bigger than a target one and prune that to approximate the performance of the target one, all right? So this, if you were to plug in the numbers in this existence result, you would need a network that's like, a billion times wider. And this was certainly not the case in practice. So I guess I have 20 minutes. Let me see, how should I time this? I'll tell you about that. The proof is actually really simple. So let's say that you have the simplest neural network possible, one weight, a multiplication. X comes in, WX comes out. And I would like to approximate that neural network by pruning perhaps a larger random one. How would I do this? So we'll introduce this sort of like, diamond gadget. It doesn't matter really much, but it's really easy for the purpose of the, explaining the idea of the proof. So that network, this diamond network I'm showing you on the screen, is going to have random weights on the left. What random weights? Like uniformly random between, I don't know, -1 to 1, assuming that perhaps W is in that range. On the right-hand side, I just have a combining layer. So all of the weights are set to 1. That doesn't really matter. You could have them being random, but for exposition purposes, let's say that on the right-hand side, all the weights are 1. So it's kind of like a combining tiny little diamond network. All right. So what would pruning be here? Well, kill everything apart from perhaps a subset. But what these authors did is they say, well, you know what? If I have a bunch of uniformly random weights, I can choose the X, I can choose the random weight that is closest to W, right? So that is my requirement to kind of like approximate W by pruning a random network of bigger size. And this is sort of probability 1-1. If you wanted to have kind of like this construction, then you need to draw 1/epsilon random weights to be epsilon close to the target weight. So it's kind of like a very simple argument that just involves like a union bound and kind of an epsilon grid on the range of numbers you're trying to approximate. But perhaps this lemma, the fact that if you were to go like weight by weight, you would need 1/epsilon, indicates why the polynomial requirement on the overparameterization is perhaps hard to overcome if you sort of stick with that proof technique. Okay. So again, you can use this. Of course, the main thing, the general theorem is much more complicated than this. You have to apply this on layers, see how, there's a bunch of things going on. But perhaps the core idea is this one. I approximate weight by weight by finding the target one in a set of random weights in the new larger network. So if you stick to this construction or this technique, then the polynomial dependence on the problem parameters is basically unavoidable. All right. Any questions on this?
So you just want to show that the random weights are a good covering of
exactly right.
Network, right.
Exactly right. So So what we basically, I want to perhaps go quickly over what we proved improving this work is that instead of polynomial subbucketization, overparameterization, you can actually go down to logarithmic. So you can actually get an exponential improvement in this bound and just require, you had D width, now you have D log D, all right? So you're like, something that's like a little, and as we know, logarithms are almost constant, right? So like something that actually is much smaller. So your original width is D, and the only thing that you need from the random network to be pruned is just to be a log factor wider, okay? And I will try to explain how we get this exponential improvement in the requirement of the width, okay?
So is this also optimal?
This is optimal, yes. There's a lot. It's optimal with regards to log 1/epsilon. Perhaps the DL may not be needed there, but the log 1/epsilon there's a lower bound for that, yeah.
And also the dependence on D is also...
The D times, yes, that is also. So the multiplication of D log 1/epsilon is a lower bound.
I see.
Yeah. But perhaps the rest could appear like additively. Yeah. So that.
Where did the lower bound appear, in that previous paper, or you?
In our paper, yeah. In our paper.
Okay.
Yeah.
Okay, I saw that. Okay.
And the lower bound is like actually on linear functions. I mean, it kind of like comes from the fact, if you have random numbers, well, you kind of like will need at some point. And you approximate like on the spectral norm, you will need that D log 1/epsilon type of
yes, so that's actually the size of the epsilon net on the unit sphere.
Exactly
that's
right.
why it's the lower bound. Yes. Okay. Very nice.
Very good. All right. So, all right. So how do we prove this? So we go back to the proof technique by Malak et al. And say, look, what these folks did is that they said, pick one of the weights, but perhaps you can use the fact that in this diamond structure, you're combining weights. You're taking a summation of whatever subset you choose. So perhaps I can, instead of choosing a single X to find the one that's closest to my target number, I can perhaps choose the best subset among all those possible weights. So in our case, pruning would be, finding the best subset or the best subset sum to approximate the target number. And changing kind of like to this mode of like choosing subsets instead of a single weight will give you an exponential improvement. And the reason for that is a really cool paper that appeared in 1998 by Luker, who was at UC Irvine, that kind of like exactly showed this thing, but for a different application. And I'll explain how we will use this theorem for our case. But here's what he said. Let's say you have a target number between, let's say, perhaps minus half. If you were to draw uniformly random numbers between -1 and 1, you only need log 1 over epsilon, or sorry, you need not only log 1 over epsilon of them to create a subset of them that epsilon approximates a target number, okay? So again, what it says is that every number within a given dynamic range can be approximated by sampling a logarithmic in the error of the approximation random variables that you need to within them find a subset that approximates the target number. All right. So the combining operator gives you an exponential benefit and a sort of gap with regards to just choosing a single weight. Okay. And I will try to explain how we integrate this sort of theorem in actually building the neural network gadget. But does it make sense to everybody? Is there any questions so far on this? All right. So I will just kind of like, state this as briefly as possible to be able to cover the algorithmic part after this. But what Luker basically, like the picture of Luker's theorem is the following. You have a target weight or whatever, and you have this diamond structure where you're selecting a subset of random weights. And what I would like to make this is, I want to approximate the target weight, if you will, by pruning a ReLU network. So you have to change the theory a little bit. So there's a ReLU version of Luker's theorem, which is saying the following. I can represent every link, every weight, as two tiny ReLU networks, right? And I mean, it's not that the ReLU network, it's two tiny ReLU activations. And I can approximate the effective function of the blue part of the tiny ReLU unit with pruning a bigger sort of like diamond ReLU network, right? And I can approximate the magenta sort of like, negative version of that ReLU by pruning another random ReLU network. So on the right, the big thing is basically just random coefficients on the left and the right, and in the middle I have ReLUs, right? So that kind of like takes us back to like the setting I want to prove something about, which is prove something about, fully connected, let's say, ReLU networks, although this extends to other families as well. You can basically, so this is kind of like a gadget. How do I approximate a single weight by pruning a logarithmic diamond, a logarithmically wide diamond sort of ReLU network? You can apply this on every single weight and every matrix in your neural network, in every layer. By simply doing, basic spectral arguments, you can sort of show that if you get the per weight requirement, that's kind of like all you need without more assumptions than the fact that perhaps the inputs are in a bounded domain. So if you do the algebra, and I would say that this is perhaps the least interesting part of the proof, you can get the epsilon sort of approximation between the target function and the random function or the random network that you're trying to prune. So if I were to recap this in just a simple statement, is that essentially any ReLU network can be approximated by pruning a logarithmically overparameterized but random network. Okay, and the randomness is not important. This can be applied to any sort of like continuous distribution as long as the support contains sort of the support of the weights that you're trying to approximate. This also doesn't tell you much about the kind of like the algorithm itself, right? This just says that at initialization, you can basically find whatever you want if you have enough of a parameterization, all right? And I want to sort of switch gears and see perhaps if that means anything for lottery tickets, but I want to see if this makes sense so far. All right, awesome. Maybe parenthesis, the cool thing is that you don't even need amplitudes, you don't even need weights. You can throw away everything and just have like random binary networks. Pruning binary networks or random binary networks is expressive enough to, express any function you like represented by a, continuous weight, fully connected network, which is perhaps interesting as well. But yeah, okay, so how is this relevant to the LTHs? Is there anything that this can tell us about the lottery ticket hypothesis? Perhaps from the theory, I mean, certainly from the theory, we know that like sparse and accurate models exist at initialization, that somehow the randomness in the weights does not limit you from like, does not limit, let's say, how rich the family of functions is at initialization if you're only allowed to choose subnetworks. Perhaps in practice, that's what you should be aiming for. Maybe what you should do is try to find a subnetwork initialization that has as much accuracy as you can. And once you do this, then fine tune with SGD. So, and I want to maybe expand on this idea in the next couple of minutes. One could argue, and I think there was a question relative to this in a few minutes ago. Well, take the EP. So by EP algorithm, I mean the Ramanujan algorithm. Why don't you take their algorithm and just fine tune with SGD? And again, the surprising thing is that the EP networks, the networks found by the Ramanujan algorithm, are not fine tunable. It's by itself a very surprising result. And if you want to kind of like reverse engineer the algorithm and potentially fix it, perhaps the reason why this happens is because at every iteration of their algorithm, they insist on a strict, let's say, recipe on what sparsity pattern the whole network, sparsity level the whole network will have. Okay. So I want to take some of those ideas and start thinking about potentially how we can find now trainable networks at initialization. And I want to talk to you now about what we call rare gems. So rare gems are basically lottery tickets that not only are special in the sense that they're better than random and they can be trained to full accuracy, but in fact, they're also accurate even before you start training with SGD. All right. So again, a lottery ticket is a sparse subnetwork at initialization, trainable to at least better accuracy than training a randomly sampled sparse subnetwork. And a rare gem is a lottery ticket that on top of it being a lottery ticket has non-trivial accuracy even before you try doing any fine-tuning with SGD. Okay, so it has an extra property, if you will. And what we saw in an experimental paper that's published for, we're going to present it in, I guess, a couple of weeks at NeurIPS, is that rare gems exist. We have an algorithm for it, and it works for CFAT and ImageNet, and perhaps it doesn't work for, I don't know, whatever, the common crawl if you were to train GPT-3, right? But at least for the cases where the previous algorithms were failing baselines, we are able to pass the sanity checks and beat the baselines. And I want to tell you about this algorithm. But I just want to take another 2-second pause to make sure that what I've said so far sort of makes sense and, you don't have any questions.
So the previous result that you show the improvement on this paper by Shamir and others. So that's also in this paper, this rare gem, or that's a different paper, right?
So it's in, yeah. So the theoretical result was I believe NeurIPS 2020, I think.
I see.
And the practical result is this year. Yeah. So it's like two. Okay. There's basically 3 papers. The one with like real continuous distribution, the binary stuff that was AI stats last year, and then the third paper is what I'm going to talk about, which is this year.
Okay, I see.
All right, so let's see. So basically, the algorithm that we use is really simple. Algorithmically, there's no innovation.
Sorry, Dimitris, there is one other question in the chat. Sorry. Yes. Is learning by pruning less data intensive? So this was, I think the question came a couple of minutes ago. Is learning by pruning less data intensive?
It's not. It basically, well, I'm not sure exactly what you mean by data intensive, but in terms of like, how fast we can converge for, with regards to the same accuracy and how many data points you need, it's kind of the same. So you don't need more data points and you don't need like more iteration. It kind of like looks like running SGD basically. It just, you sort of do it on a different objective, if you will, and with a different set of variables as well. Very good question. So the algorithm we are actually running is very similar to EP. So I'll tell you what the algorithm is. So here's what we'd like to minimize. I want to minimize the loss of my masked random network. So I start with random weights, W0. I assign, think of it as probabilities P, or scores P with every weight. And those scores are going to be between 0 and 1. And at the forward pass, I'm just going to round them. So just like, you know, the rounded version, if you will, or the thresholded version of the score is going to be used as the actual variable that's going to maintain or kill an edge. And the rounding function can be whatever you want. It can be like randomized rounding. It can be just like, you know, deterministic rounding. And we tried all of them. They're kind of like all of them are the same. So we just choose the very simple one, which says take your p variables that you're optimizing, and just if they're more than half, just threshold them to 1. And if they're less than half, threshold them to 0. Very simple algorithm. So P is what you optimize. There's very well-known techniques to, like, you know, again, do the back prop pass with like using the straight through estimator. The only thing that this is not controlling is the sparsity. To control the sparsity, there's simple ways of sort of doing it. The one is the following. If a score P becomes really low, threshold that weight, freeze that weight always to be 0. And also regularize with L to norm the probabilities P. And that helps balance or maintain a particular sparsity that you like. And again, algorithmically, there's nothing new here. Perhaps, you know, I haven't been really doing compressed sensing back in the day, but like, you know, this looks a lot like a lot of the compressed sensing algorithms people were using in, you know, the related literature. And what's surprising is that this simple algorithm actually works. And I want to try to convince you in the remaining 2 minutes that this works. So I will just show you this table, right? So this table is basically telling us kind of like all the pruning methods for finding lottery tickets, whether they prune at initialization or a little bit after initialization, whether the networks that they find get better when you do SGD on them, and whether they pass sanity checks. And the only thing that passes sanity checks is IMP, Frankel's algorithm, if you prune a little after initialization. And the only algorithm that we know, at least so far, that passes those sanity checks and the baselines is the one that we introduce in this paper. And perhaps the interesting thing that is about this algorithm is it's also much cheaper than IMP and many of the other methods that have presented in the past literature. The reason I'm relatively comfortable making this table and this statement because we tried on a bunch of networks and a bunch of data sets. We didn't try on every single data set that exists out there, so there may be cases that this algorithm does not work. But as far as we know, the baseline set by the community so far, we were the first ones to pass them. So this simple modification, perhaps of EP, based on the idea that at initialization, there's interesting things that you can find, seems to work very well in practice. I have a bunch of other experimental results I would like to share with you, but I think we're a little bit short on time, right? So Arya will have like maybe 1 or 2 more minutes. How is it looking?
Yeah, sure.
Okay, so I just want to conclude with perhaps a bunch of open questions. So there's been a lot of study with regards to existence results for lottery tickets. We perhaps have some understanding on what's happening at initialization, but algorithmically, in terms of like theoretical results, there's basically nothing. There's a lot of interesting questions people can be thinking about, that perhaps there are architectures that are more amenable to pruning than others. And this whole literature has had me think about, maybe there's ways of training without just doing SGD on the weight. So maybe there's perhaps a back propagation of free training framework that may be better or different for sure than SGD. And just that, I think, at least for me, is intellectually stimulating to just think about. I just want to end with, having you maybe think about, all these other different flavors of sparsity and sparse tuning that exists, especially in the context of like large language models, which my group has been thinking pretty intensely about for the past 6 months. So for these huge models like GPT-3 and whatnot, there's a lot of things you can do to fine-tune them to have good accuracy. So you start with like a frozen model. It's not random anymore, but somebody hands it to you. And they say, well, you can take this model and fine-tune it for some downstream task of interest. There's many ways of you doing it. So you can tune just a sparse subset of weights, or you can do low rank updates, tune only the biases or only the batch norm parameters. And all these methods seem to kind of like magically work, but we don't really understand how well they work. And, there's no theory for them, and there's not even a good experimental study that can like compares all these different flavors of sparsity. So yeah, with that, I just want to conclude and perhaps take any questions if there is anything lingering. But yeah, thank you so much for being patient with me and for all the great questions.
Thanks, Dimitris. Let's see if we have more questions. We have a lot of questions during the talk, so it's very interesting. So I think there are more questions coming in the chat. So let me just read them one by one. So there is one question from Paolo. Nice to see that. It's probably like more of a comment. Nice to see that you need only L2 for keeping the sparsity. Okay, Dimitris, you want to comment on the comment?
Yeah, so this was one of the first things. So like when my student said L1 didn't work and we used L2, I'm like, why? And the answer is like, we have no idea. So perhaps because the scores are between 0 and 1, L2 is good enough. But yeah, I don't have, I mean, usually L2 is bad when you have like, you know, it makes large entries larger, right? So if you're like kind of like in the above 1 regime, but beyond that sort of straightforward, obvious thing, I don't have anything more intelligent to say.
Okay, so then there is one other question over here. P is learned with training weight. P is learned with training, right? So yes. It is pruned in the training process.
So you train, so the way to perhaps think about is that there is like, you know, the set of random weights that you never change apart from setting them to 0. And there's maybe like a ghost network that lives on it. That ghost network has P parameters and you train those P parameters. So there certainly is training and learning that happens. It just happens on a separate set of variables. And at the end of the day, the network that you're using is a subset of the random network that you start with. But the way that you do this is, of course, involving training, but just something else, not the weights.
There is one other question from Harsh. Can these rare gems be found after training with SGD with some suitable parameters?
Yeah, that's a great question. We've tried this a little bit with language models, pre-trained language models, but we haven't been very successful. Perhaps because for language models, sparsity is not, or like unstructured sparsity is not the choice of simplicity, if you will, like low rank methods are better there. But for the cases, like, you know, for CFORT and ImageNet, from some preliminary experiments that we ran, it seemed to be the case that, like, you know, doing a little fine tuning, like, you know, a little warm start didn't really help, but you can still do it and you get similar performance.
A follow-up question from Ilan regarding this this previous question, right? It says, so strictly speaking, it is not pruned at initialization.
So ours is, yeah. So I mean, it depends. I don't know what strictly speaking mean, but like, you know, there is a random network. There is a black box that does whatever, and that black box spits out a subset of the subnetwork. Oh, sorry, a subset of the weights of the original network, right? So pruned at initialization doesn't really mean that, you know, you don't do, like, you know, you don't train or whatever. But perhaps if I were to like reformulate your question, is it like, do you win anything computationally by doing this at initialization? Currently, computational speaking, our algorithm is competitive with sort of like, you know, the fastest algorithms for pruning, even those that kind of like, you know, prune while training or whatever, but it doesn't omit, like, you know, you still have to deal with training or like learning something at initialization. And there's the meta question of like, you know, forget about what you do and how you do it. I'm assigned a number of compute cycles. What's the sparsest, most accurate network that you can give me? All these algorithms are very competitive to each other. So it's not, you know, it's not really clear to me, at least, how much compute I can save, at least during training, in my effort to produce these sparse models.
Okay, I think this was a very interesting talk, Dimitris. I will just end this with you know, a non-technical question. So there seems like throughout the talk, I found like there are quite a few really nice theoretical questions that, and you have like listed at the end as well. But one, like, I don't know how you do it, but look at this, all these large language models and this number of parameters. I think one barrier for many, you know, theoretically minded faculty and students to start working on this, that we think, okay, I may have something nice to say about this, but then I have to do something with this very large model and like, billions of parameters and thing to make it palatable to all the practical people. Like, is that something that you face, or you have found a way to?
Yeah, basically, I guess the one informal thing I can tell you is the following. Like, this paper costed around, I don't know, like, $10,000 or whatever in experiment. So like, you kind of like have to do the experiments, and like running them either requires buying GPUs or running stuff on AWS. For vision models, it's still doable. If you want to do stuff for like really large models, GPT-3, it's not possible. But there are models like GPT-2 and BERT where you can still do some form of training. But it's, so the experiments is not only to convince like practitioners, but I think they also act as a guiding, if you will, light as to what I should be proving and what should I be thinking about, right? So it's kind of like perhaps a twofold, like, it's useful for both of those things, perhaps.
Right. Oh, this is great. Like, and I think you are navigating this really nicely, being an information theorist. Thank you so much for the talk. And I think there will be more questions. If there are any, I will send them your way, or people will directly reach out to you. Thanks a lot for coming.
Thank you so much for attending.
Yeah, giving this
inviting me. And hopefully, I don't know if any of you are going to be at New Orleans in a couple of weeks, but hopefully I'll see some of you there.
There will be few people from